Okay, YouTube, in our last video we started to discuss the concept of a limit, but in this video we're going to formally define what we mean by a limit here. And so let's go ahead and start by looking at the definition of what we call a limit. We say that if our function, or our y value here, f of x, becomes arbitrarily close to a unique number L, and so unique, this is like individual, okay? It's not like it gets really close to two different numbers, but as it gets really close to a single y value, and we're going to call this capital L, so this is our limit here. As x approaches some value, and we're going to call this value c, from either side, then we would say that the limit of f of x as x is getting really close to c is L, and this is how we kind of write it right here. So picking this apart, essentially, let's go ahead and pick out a few things here. We say that this capital L, this is our limit. And this is basically, if we want to look at it this way, we say the value that f of x is approaching is getting really, really close to. And so this idea of approaching, but maybe doesn't get there, is going to be really important. But we say that this is our limit, and we say that f of x, this is our function. Okay, so of course this is the function that we're looking at here, but these are really just a y value. And so we're really asking, what is the y value of our function getting really close to? And this is this value L here, but as our x value gets really close to c. So let's write a little note here. We say that this is c value right here is the x value that our function is approaching. And the important thing here is that we approach this x value from either side. So what we're going to look at really in this video is really just looking at what our function is getting close to as we start plugging in x values really close to this indicated x value here that we're calling c. And so in order to answer this, what we're going to do is we're really going to start to utilize what we have often utilized, which are tables and graphs. So let's go ahead and take a look at our very first limit here. And what we want to do is use a table to do this. So I've kind of already set ourselves up here. So let's go ahead and take a look at our limit. It looks like we have this right here. We say, what is the limit of 3x minus 2 as x gets really close to 2? So as we read this right here, we're saying that we have some function, and our function in this case is this 3x minus 2, which is some linear function, okay? So I do want to make a note of that here. There's some linear function. We're saying what are our y values getting really close to as our x value gets really close to 2. So in order to evaluate this on a table, what we're going to do is, first things first, we're going to go ahead and plug our function in for y equals on our calculator here. And so we say 3x minus 2. And in order to get a table, just right behind graph here, it does say table. If you go to table, it should pop up a table for you. Now, what you're going to see is that what we're trying to figure out is what our graph is getting really close to as x gets really, really, really close to 2. So in order to determine this here, I certainly could go to where x equals exactly 2, but if you'll notice in my table here, what you'll see is that we have 2 smack dab in the middle, and as we go to the left and right of this, we're seeing 2 very close x values to 2, one that is 1/1000th before 2 and 1/1000th after 2 on the number line. But then we also see that these are just a little bit further apart. These are 100th away in each direction, and the 1.9 and the 2.1 are a 10th away in each direction. So we're often going to set our table up this way. So in order to find out what these values are, what my suggestion is put this in, and instead of going to table first, let's go to table set, and the x value that we always start our table at, let's just go ahead and make it the x value for which we are evaluating this limit. So we are asking, what are our y values getting close to as x is getting really close to 2? We'll go ahead and start our table at 2, and my first stop would be to put this at 1/10th in gap width, okay? So when we go back to our table here, we're going to start at 2, and I'm going to scroll up a couple times here. We can see that 1.9 is just before 2, and 2.1 is just after 2. And we see that at 1.9, we're at a height of about 3.7 on our graph. And as we go back to our calculator here, at 2.1, we are at 4.3. So what we're going to do is we're going to go back now, and instead of going by a tenth of an x value at a time, or an interval, we'll say go to a table set starting at 2. Okay, we want to start at 2, always at the value for which we're evaluating the limit. And this time we're going to go by 0.01. So we're going to be going really, really close to this x value of 2. And if I hit up once here, we see at 1.99, our graph is at a function value of 3.97. And if we were to go to now 2.01, we'd be at 4.03. So 4.03. Now next we'll go to an increment value or a delta value here of 0.001. We'll go by 1,000th, and we'll again start our table at 2. But if I go back to my table now, and I'll scroll up one, we say 1.999 is 3.997. So we get 3.997 here. And what we end up with here is 4.003. So what we're trying to do is support with our table here, what is the x value that this is continuously getting close to from either side. And what we notice is even if we come from the left side of 2 or we come from the right side of 2, our graph is getting really, really close to a value of 4. Now you might ask yourself, can't we just say that it's at 4, at 2? And you'd be correct in saying this, but what we wanted to do was explore this excuse me, with a table of values. So now what we're going to do is we're going to graph this function. And so to graph this function, we do know that this is a linear function. And so I'm going to go back to my I guess calculator here. I'll go back to y equals. Once you get this in, I'll hit zoom 6 just so that we have a standard window. But what we're going to see here is the graph of this equation that has a y-intercept at -2 and a slope of 3. So up 3 over 1, up 3 over 1, up 3 over 1. What we want to do now is kind of say, how would the graph support this conclusion that we got over here? And so what I'm going to do is pull out my trace menu here. And as you see this, basically is we trace to an x value that's getting close to 2 from the left. Okay, so we're getting closer and closer and closer and closer to 2. Okay, just before 2, you can see that our y values, they start small, but they're starting to get really close to 4 as x gets close to 2. And as we come from the right side here, we can see that our graph is getting close to 4 from there also. So for at least this example right here, what I want to do is I actually want to sketch this out. We're going to say 1, 2, 3, 4, 5. We'll go down 2, draw a dot. We say that this is 0, -2. But we'd go up 3 over 1, so we would be at a height of 1, 1. And we'll go up 3 another 1 over here. And we say that this is our point right there. So what we're basically highlighting on our graph is this. And I'll switch colors here just to be clear on this. To answer this limit question, we're saying that as our x values are getting really, really, really close to 2 from the right and from the left, okay, what we're seeing is that our graph, our y values are getting really, really, really close to this y value right here. And so what we're going to do is we're going to label this right here. We're going to say that that right there is the limit, or that is the value that our graph keeps getting closer and closer to as our x values kind of zero in on this value of 2 right there. So for this next example, let's go and take a look at it. We're going to look at an example here where we again want to use a table to evaluate this limit, but I've left the table a little bit more sparse. So let's go ahead and start with this. Our limit that we're looking for is the limit of this function here as x is getting really close to 0. So what we'll start with is we'll put 0 right here, and we'll start very, very close to 0. We say 0.001. This will be negative 0.001. And then we'll go by a tenth. We say 0.01. negative 0.01, and then over here we say 0.1 and negative 0.1. Basically, what we're going to do is we're going to go around both sides of this at x equals 0. Now, one thing that I want to point out is that our function here is actually equal to x over the square root of x. Let me fix that radical there. We say over the square root of x plus 1, that quantity minus 1. So if we were to actually plug in 0 here, the interesting thing is we get 0 over the square root of 0 plus 1 minus 1, which actually gives us here 0 over the square root of 1 minus 1, which is 0 over 0. We're going to give this a name here. We're going to call this indeterminate form. Indeterminate form, which means that our function actually doesn't even exist there, but we can still find a value that our function is getting really, really close to from either side. So getting our calculators rocking here, let's go ahead and type this in for y equals. So clearing this out, we have x divided by, all in parentheses here, and then we'll put in a square root. We have the square root of x plus 1, that minus 1, and we'll cap off our end parenthesis here. If we now go to table set, we want to start our table at, well, it looks like x equals 0, and we're going to go by just tenths. So we say 0.1, so fairly close to this. If we now go to table, we're going to see some things here, starting with the fact that exactly at 0, we see that we get that undefined value. So we don't know what it's exactly going to equal there because it doesn't equal anything. But if we go left by a tenth, we have 1.9487. So I'm going to put this in here. We have 1.9487. And if we go above 0 by a tenth, 0.1, we have 2.0488. So 2.0488. Now, as we go back to our calculator and we change our table set to, again, start at 0, but this time go by 0.01s, and we go back to our table, and I'll hit up once here. We can see that negative 100th, we're at 1.995, so we have 1.995, and over here, I'm going to venture a guess we have 2.005. Let's go back and look. We certainly do, and then going back to table set one last time, we're going to set it back to start at 0, but this time go by thousands. And so going back to our table, we can see that as we get really close to an x value of 0, our function's getting really, really close to, let's see, 1.9995, 2.0005. What we can see is that as x is getting really close to 0, our y values, even though they don't get to something, they get really, really, really close to what? And it seems to me that we're getting really close to a value of 2. So we would say that the limit here is equal to 2 because that's what our y values are getting extremely close to, as x is getting arbitrarily close to 0 from either side. Now, with respect to our graph, I want to make special care that we take a look at this graph here. I'll hit graph, and what we see is this square root-like looking graph. And so in terms of justifying this here, again, we could hit the trace key, and what you're going to see is exactly when x equals 0 here, it doesn't even list a y value. But that's not to say as we go to the left here, and as we start getting closer to 0, you look how our y values are getting really, really close to 2. And as we go to the right of an x equals 0 here, we'd say from the right we can see our y values getting really, really close to 2. So to get a better picture here, let's do this. Let's zoom in. And I'm going to take my little zoom in cursor that's at 0, 0. I'm going to scroll it up to about right around here on my undefined point on my graph. We'll go up here. Okay. So now if I trace over, we could see that right now we're getting really, really close to 2 from the left and really, really close to 2 from the right. We could zoom in even further, and as a matter of fact, if I can go to format here, I can even turn my axes off. Just to show you that, as we turn our axes off here and we graph this again, you'll be able to see, and it's kind of really, really small. Right here there's a little undefined spot. But what we can see with this is that our graph, okay, as we do this, even though it has a hole right here, as our x values are getting really, really close to 0, our y values are getting really, really, really close to that y value right there. And so the limit here is equal to 2, and our graph supports this because we can see that from both sides of an x value of 0, our y values are approaching a single y value that we're calling our limit. Cheers.